On this, we go through the major components of a storage array so that we know what they look like and we get an idea of how they work internally. Storage arrays are tin or boxes. In fact, it used to be common for us to call the big monolithic arrays big iron. So we'll go with the idea that they're boxes. Boxes in the same way that servers are boxes. Let's throw a box on the screen to start things. This is our storage array. It's pretty simple, right? Or at least by the end of this slide, we'll have transformed this little box into a fully fledged storage array. First thing we need to do, to the left of our array, is show our network and our attached hosts. At this point, we really don't care about the type of network or the protocols that the host uses to connect to the storage array. It could be SAN or it could be NAS. Right now, it doesn't matter. Next, we'll add some network ports to the front end of our array, and we've added 4 of them. By the way, we call these ports front-end ports to distinguish them from back-end ports, which we'll talk about shortly. And as we can see, these ports physically connect to our shared storage network, and they're known as targets or target ports in storage parlance. Each of our hosts also has network ports, which they use to connect to the same shared storage network. And in storage parlance or storage lingo, these are referred to as initiators or initiator ports. Basically, the initiator sends commands and requests such as read this, write that, to targets, and targets respond. Anyway, back to building our storage array. Behind these network ports are CPUs. These CPUs run the firmware or the microcode that is the brains of the storage array, and they're usually x86, x64 CPUs. Behind the CPUs is cache memory. Cache memories in storage arrays are almost always non-volatile, and by that we mean that you can hit the big red emergency power off button in your data center, cutting the power to your array and everything else in the data center, safe in the knowledge that the data held in cache memory won't be lost. Now, you would of course almost certainly lose your job, and you'd probably face criminal charges if you did this, so don't do it. But the point is, storage arrays make sure that data stored in RAM cache is protected from power failures. These caches are often DRAM based, and they're used as read and write caches. The objective of the cache is to speed up read and write performance, especially write performance. And believe me, cache memory makes the world of difference on the performance front. Now, behind cache memory are the drives. We usually refer to the drives as being on the back end, and the network ports and cache memory as the front end. Now, depending on your array technology, this diagram can be a little more complicated, obviously. But it's looking good so far, but there's still plenty for us to do, so let's now dissect our array down the middle. This line that we've added represents a failure boundary. So, a failure in any of the components above the dotted line will not cause the array to fail, because the components below the dotted line will pick up the slack and take over the responsibilities of the failed components. What we now effectively have is 2 computers coupled together as a cluster. We'll call each of those computers controller A and controller B. If controller A fails, a power loss, catastrophic hardware failure, whatever, cluster B will remain up and keep servicing I/O. And this is probably a good place to point out that most back-end drives will be dual ported, meaning that they connect to both of the controllers in the cluster. So if one controller fails, the other one can still access the contents of the drives. And while we're on with drives, let's also decouple the drives from the storage controllers, giving us our true back-end. Drives in storage arrays are housed in external chassis called drive shelves or drive enclosures. These enclosures connect to the controllers via the SAS, SATA or fiber channel connectivity technologies that we mentioned earlier. Each drive enclosure is attached to both controllers in the cluster, so that, as we mentioned, if a single controller fails, the surviving controller still has access to all of the drives on the back end. And hey, presto, what we've got on the slide is a classic dual controller storage array. Basically, 2 controllers, sometimes called heads or nodes, on the front end with their own network connectivity, processing power and non-volatile cache memory, connected to the back-end drive enclosures via redundant connections. Now then, for a little more detail, the connectivity to the drives on the back end is usually active-passive, meaning that only one port on the dual-ported disk drive is active at any one time. Also, external drive enclosures usually have a small amount of processing power and run their own firmware that reports on things like environmental related conditions, like power, cooling and failure conditions. SCSI enclosure services, or SES, is a common protocol and system used to monitor and manage drive enclosures that house SCSI-based drives such as Fibre Channel and SAS drives, and all good storage arrays and drive enclosures implement some form of SES, SCSI enclosure services. The network ports on the front end and back end are almost always standard PCI expansion cards installed into the controllers. If your front end is Ethernet based, like it will be for NAS and iSCSI SAN deployments, if you were to pull the lid off your controllers, and of course don't do this with the power on and while your system is servicing I/O, and definitely don't do it if you don't know what you're doing, but let's say you do know what you're doing, what you would see is that the Ethernet ports are on standard PCI expansion cards. The same goes for Fibre Channel ports, they're also standard PCI expansion cards. And again, the same usually goes for the back-end ports. If you've got a SAS back-end, you'll see that the SAS ports are housed and mounted on standard SAS PCI expansion cards. And finally, before we move on to the next concept, all LUNs, volumes and file shares are exported out of and accessed via the front-end ports. So no front-end ports, no shared storage. Now, let's have a bit of a dig deeper into dual controller architectures.